Hello everyone, my name is Yashta Shekhar and today I'm going to tell you about construction of a binary tree from pre-order and post-order traversal. Here we go. First of all, what is traversal of a binary tree? To visit each node in a given binary tree exactly once. The given traversal techniques are divided into three types: in-order traversal, pre-order traversal, post-order traversal. Pre-order traversal. In pre-order traversal, we visit root node to visit left subtree of a root node to visit right subtree of a root node. Post-order traversal. To visit left subtree of root node to visit right subtree of root node to visit root node. And here these are the steps. Introduction. Binary tree traversals. In pre-order, first there is root node and then left subtree, then right subtree. In post-order, first left subtree and then right subtree and then at last root node. Here we have a problem statement that can we construct a binary tree uniquely using only pre-order and post-order traversal? Binary tree uniqueness. Not always uniquely possible. Unique if tree is full binary tree, such that each node has 0 or 2 children, and why? Pre-order gives root node first, and in post-order it gives root node last. It arises in some structures ambiguously. Here are the assumptions that the binary tree is a full binary tree. Both pre-order and post-order arrays are available. All node values are unique. Here are the example input: pre-order and post-order 1, 2, 4, 5, 3, 6 and 7, and post-order 4, 5, 2, 6, 7 and 3 and 1. Recursive approach algorithm, and here there are few steps. Start with root node from preorder. Find left subtree root in preorder. Find its positions in postorder to identify subtree boundaries. Recurse for left and right subtrees. And here is a base case: if start index is greater than end index, then it returns to null. Pseudocode: construct pre-post pre-index post-start post-end. If post-start is greater than post-end or pre-index is greater than or equal to length of pre, return none. Root is equals to new node pre of index, and pre-index plus is equals to -1. If post start is equals to post end, return root. Left root value is equals to pre of pre-index. Index is equals to find its post, find in post, post start, post end, where value is equals to left root value. Root left is equals to construct of pre, post, pre-index, post start and index. Root right is equals to construct of pre, post, pre-index, index plus 1, and then return root. Walk through an example that here are the pre and post order examples, and here we are going to show about show tree construction step by step. And this is the final tree structure, and here is one is the root node and two is lesser compared to 3, so it is left subtree, and 3 is the right subtree, and here are the childrens of the 2, and here are the childrens of the 3, and these are called as right subtree, left subtree's childrens. And here we take an example: pre and post order. Here pre-order is plus, minus, a comma b star c division d e, and post. These are the examples. First, here we take root node as plus. For in pre-order, first one we call it as root, and in post-order, last one we call it as root node. So here, and these are the left subtree and these are the right subtree one. And here in post order, first ones are left subtree one and last ones are right subtree one. Left subtree. And these are right subtree. And here these are right subtree. And here these are left subtree. This we call it as root node. And here we call plus is called as root node and we do split into two. And here as these are the left node ones, here we take this minus as a left subtree and here the again it's gonna split and here it's gonna be A and here it's gonna be B. And here we take star as the right subtree and its tails are C and slash. And again slash has two more children and they are called as D and E. First we write here we write root node and then we write left subtree and right subtree and in left subtree we write the children part and in right subtree we write the children part and here we have two more children, so these are also children and the last two left ones are called as leaf nodes. Time and space complexity. Time complexity mm, due to repeated search in post order. Optimize it to 0 of n using hash map. Space complexity 0 of n for recursive stack and tree nodes. Conclusion: binary tree can be constructed from pre-order and post-order if it is full. Recursive construction leverages known traversal orders. Optimizations possible with hash maps. Thank you.